Welcome to CS 1401 Video 18.1. Today I'll discuss iteration versus recursion. Computer science is about solving problems. Often, to solve a problem, we solve an abstraction of the problem. For example, suppose we have to sort a list of numbers, say 2, 5, 3, 8, and 1. Instead of designing a program to sort this specific list of numbers, we would usually design a program to sort any list of numbers, which means a list of any size. Suppose now that we have to navigate through a maze. Instead of designing a program to find the exit of some specific maze, we would usually design a program to navigate through any maze, which means a maze of any size, any configuration. Now, given that we often find ourselves designing solutions to these abstract problems, it's hard to know in advance how many steps of computation need to be carried out. 4, 7, 53, 2 billion? This number depends on the nature of the algorithm and the size of the input. So instead of programming, say, 4 steps of computation, we need to be prepared to repeat these steps a number of times that is not known in advance. In some cases, we may have information about this unknown number. It might be, for instance, the size of the list in the sorting case. In other cases, we may not know how large the unknown is, but we may know the condition under which we need to continue repeating a process. For example, in our maze application, we need to continue repeating until we have reached our destination. This video is all about the repetition of steps. More particularly, it's about repetition as iteration and about repetition as recursion. These are different approaches to solving problems that involve repetition of steps or processes. I want you to understand how to solve a problem by breaking it down into a series of smaller steps and which approach to use. By now, in this course, you know about iteration and you know about recursion. I'm going to look at several problems that illustrate the value of each approach and that illuminate their differences. In this video, we'll look at linear search and at calculating Fibonacci numbers. In the next video, we'll look at binary search. Let's look first at the problem of linear search. Linear search consists of looking for an element within a list of elements. To make it simple, let's say that we are looking for a particular number in a given list of numbers. Let's say that this list of numbers is stored in an array, but we don't know the size of this array in advance. Okay, let's look at ways to solve this problem. Quite naturally, given that the list of numbers we have is an array, we can simply go number by number through the list, one at a time, and return true if and when we find the element you're looking for, or false otherwise. Going one by one through the numbers in the array sounds like a highly repetitive process. Here's my idea for the algorithm. Do the following for each element in the list. Go to an element in the list. Check if it is the desired element. If so, return true, and otherwise move on to the next element. Then, if we've looked at all the elements in the list and haven't found the one for which we're looking, return false. This highly repetitive process fits the profile of a repetition, which is what brings us to use iteration or recursion. Now, looking at the process I outlined above, iteration seems somehow a natural fit. We are going to repeat the same process a known number of times, and this number of times is the number of elements in the list. So here goes as a pseudocode algorithm. And here's the loop control, int I equals 0 will be our start. We'll loop as long as I is less than list.length, and after each execution of the loop body, we'll iterate I by 1. The loop body is if list sub I is equal to the desired element, then we return true. If we get through the entire loop without returning true, which means we haven't found the desired element, then we return false. This is iteration. We are repeating a process for a given and known number of times, in this case equal to the length of the list. Now, if we were to reconsider the solution of this problem to make it recursive, what would we need to do? Recursion involves a method calling itself over and over again until a stopping criterion has been met. For the linear search problem, what will need to be repeated is the part of the algorithm that checks the current element of the list. Check if it is the desired element. If so, return true, and otherwise move on to the next element. As a result, the method we could be calling recursively could be checkElement, which takes an array of elements, an index to know which element to check, and the value of the element we're trying to find. Given this, we can write a recursive algorithm in pseudocode to solve our linear search problem. CheckElement takes the array we're searching, the index of the current element at which we're looking, and the element we're looking for. The body of the method is that if the index is greater than or equal to list.length, that is, we've looked through the entire list, then return false because the element isn't in the list. If the list subindex, that is the one we're looking at now, is equal to the desired element, return true. Otherwise, we'll call checkElement on the same array. We'll increment the index by 1, and we'll have the same desired element, and that's our recursive call. As you can see, although this program produces the same outcome as the iterative one, it is a little less elegant, not as natural. Even if the list of numbers were represented by a linked list, we might still come to the same conclusion about iteration versus recursion for linear search. Here's a pseudocode implementation of recursive linear search for linked lists. CheckElements takes one argument, which is the goal element. If the data field is equal to the desired element, return true. That's a base case. If next equals null, well, that means we've reached the end of the list, and we return false. That's another base case. And otherwise, we have the recursive case in which we check element of next. And here's a pseudocode implementation of iterative search for linked lists. For node n equals head, in other words, our iterative loop starts pointing to the head of the list. Our condition is that n isn't null. And every time we go through the body of the loop, for the next iteration, n will be equal to n.next. And the body is quite simple. It's if n.data equals the desired element, return true. And if we've gone through the entire loop, then we haven't found the element, so we'll return false. Next, let's look at our second problem, calculating Fibonacci numbers. As we learned in class, the Fibonacci numbers are an interesting sequence of numbers that follow a really simple rule. Assuming that we call the ith Fibonacci number f sub I, then we have the following. F sub 1 equals 1, f sub 2 equals 1, and f sub n equals f sub n minus 1 plus f sub n minus 2 for n greater than 2. As we observe in the definition of the numerical sequence, computing the nth Fibonacci numbers requiring knowing, and thus computing, the n minus 2th and n minus 1th Fibonacci numbers. This means that if we have a method to compute any given Fibonacci number, say Fibonacci of int sub n, that computes the nth Fibonacci number, then right away we can apply the recursive definition of Fibonacci in a programming design. Our Fibonacci method will return an int, and it takes int n as its argument. If n is equal to 1, return 1. If n is equal to 2, return 1. And otherwise return Fibonacci of n minus 1 plus Fibonacci of n minus 2. Here we go. We have a very elegant design that sticks perfectly to the definition of Fibonacci numbers. This is a recursive approach because the calls by a method to itself are necessary to obtain the final result. Now, if we want to design an iterative solution to this problem, we have to build explicitly each number that comes before the desired Fibonacci number. This means that we are going to need 3 sliding variables, which I'll call aux1, aux2, and aux3, and the process is going to be as follows. Int aux1 equals 1, and this is going to represent f of I minus 2. Int of aux2 is equal to 1, and that's going to represent f of I minus 1. And int of aux3 is also going to be equal to 1, and that's going to represent f of I. Here's the loop body. We'll initialize I to 2. As long as I is less than n, and that means we're going to start as long as n is 3 or greater. Why? Because we know that f of 1 is 1 and f of 2 is 1. So as long as n is 3 or greater, we'll execute the body of the loop, and every time we execute the body of the loop, we'll increase I by 1. The body of the loop is that aux3 will be equal to aux1 plus aux2. In other words, we'll slide the values of those two into aux3, and we'll slide the value of aux2 into aux1. And we'll slide the value of aux3 into aux2. Finally, we'll return aux3. This iterative approach is still fairly simple, even if it doesn't directly follow the definition of the numerical sequence. It turns out that the iterative approach is much more efficient than the recursive version, even if the recursive approach is much more intuitive. We can see the reason for this in a tree diagram of the recursive algorithm. The diagram shows the tree of the recursive calls and processes that are executed to complete the 5th Fibonacci number. Looking at the tree, we can see that to compute even this simple Fibonacci number, f of 5, the algorithm makes many redundant calls. For example, Fibonacci of 3 is called twice instead of once, and Fibonacci of 2 is called 3 times. In contrast, the iterative approach computes each Fibonacci number only once, which makes it a far more efficient algorithm. The iterative algorithm executes in linear time. That is, the number of steps is a linear function of n, while the recursive algorithm executes in exponential time. The number of steps is an exponential function of n. You will learn much more about this sort of thing later in the computer science curriculum. For now, it's probably enough to note that for Fibonacci of 1000, the iterative algorithm executes a number of steps proportional to 1000, and the recursive algorithm executes a number of steps proportional to a 300-digit number. So, in this video, I've compared iterative versus recursive algorithms for linear search and for computing numbers in the Fibonacci sequence. In video 18.2, I'll compare iterative versus recursive algorithms for binary search. See you shortly.